question is, what does D of n look like? Now, we built this in class already with Cheb.m. Remember, Cheb.m does this. That was the past, which is the future. Okay. Whereas it was the, yeah. Anyway, you know how it is. So let's figure out how to build this matrix. And I'm just going to basically, I'm not going to go through all the details of it because it's kind of long-winded. But I'm going to show you what this differentiation matrix looks like. It's constructed out of polynomials. And by the way, I'm not going to connect this to the cosine transform in this lecture. All I'm going to do is show you how to represent this. How does it look on the domain of Chebychev points? Okay? So and let me just show you what this matrix looks like. So the dn, the 0th component is that. Last component, this. Let me tell you what the diagonals look like. And then let me tell you what the off diagonals look like. CI. All right, let me tell you what C is. Okay, C is j is 2, where j equals 0, and or n, and Cj equals 1 otherwise. Okay. By the way, how did I get these things? So let me tell you the root of it, Lagrange polynomials. I told you there was a way to say, give me a number of points. One way, say, if I have a polynomial and I want to go through a certain number of points, one thing I could do is just set up an ax equals b problem, right? I have this many unknowns, this many constraints, set it up as ax equal to b, I get a result. It costs me order n cubed to do that. Part of what we want to do is get away from paying such high prices for doing computation. The Lagrange polynomials are sort of ideally suited for getting yourself a formula for a polynomial that goes through a prescribed number of points. Okay? It's a very simple, many ways, very simple idea. I can actually sort of highlight it here real quick. So the Lagrange polynomial does something like this. So say, suppose I have something, 2 points I want to go through, x naught, y naught, x1, y1. I just want a polynomial that goes through that. Well, how would we normally write this down? Well, we would say, hey, how about if I make up a line like this, right? And I'd say, oh, so I would have 2 equations, 2 unknowns. I could solve it 2 by 2 by making it go, put in x naught, y naught, put in x1, y1, solve the 2 by 2 system. Alternatively, I could just say, well, I can write that down pretty easily. I can just say, what are the points that I need to go through? I have x minus, let me just try to get this right. Without doing any algebra ahead of time, I can just write it down. Oh, hold on. There and I'll tell you what I just did. Here's what I did. I wanted to go through y naught and y1. So what I want is at x naught. How about if I put in x naught, I want this thing to come out as y naught. If I put in x1, I want it to come out as y1. So if I put in x naught, I want this to be 1, that to be 0. If I put in x1, I want that to be 0, that to be 1. And then I just do that. I just said, look, if x naught is in here, I have x naught minus x1 over x naught. Okay, so there's a minus sign. Let's do this. I knew I wouldn't quite write down right. So if I put in x naught here, I get x1 minus x naught, x1 minus x naught. They're the same. That becomes 1. becomes x naught. And by the way, if I put an x1 here, so x naught here, x naught minus x naught is 0. Okay, now let's go look at x1. At x1, I have x1 minus x1, 0. x1 minus x naught, x1 minus x naught, that's 1, I get y1. I didn't have to solve a 2 by 2. You could just generalize this. You have n equations. You have certain xn that go through yn's. Lagrange polynomials will let you write down the answer immediately. Here's the polynomial you need. You don't have to go solving an order n cubed system. That requires you to solve an order n cubed system. Lagrange just said, here it is. And by the way, this is nice because it's algorithmic, right? You just say, oh, okay, so now I can just put in an algorithm, solve it out, done. Right? Very simple for your computer. No setup, no order n cubed. Just here's the polynomial. That's the idea you use in constructing this D matrix, which is the differentiation matrix.
The essential catch of the D matrix is that the delta x's are different, and that's why it's different from the other.
That's right. Yeah. In fact, here this takes into account explicitly the non-uniform spacing of this thing. In fact, let me write down the matrix D in sort of a more graphical way. So your D of n I don't even know if it's worth doing this, but let's do it. I've already committed. Those are the corners. And here on this first row, here's what the first row elements look like. Bottom minus 2 minus 1 n plus j 1 plus x of j. Okay? I is the row, j is the column. So as you go across the column, right, this will change. Different columns here. Okay? And then down the diagonal, you have net of negative xj, 2 over 1 minus xj squared. And then in the other areas, you have minus 1 to I plus j over xi minus xj. Okay? Here, you can start shaping up what this matrix looks like. This is using non-uniform spacing, Lagrange polynomials to create it. And so effectively what you're using is these Chebychev points with these Taylor expansions of the Lagrange. Okay? So that's what your D of n looks like. And by the way, when you go build this here, that's what Cheb.m builds. Cheb.m built this for us. So the nice thing is you don't have to worry about it. You just say Cheb and throw in the number of points. It brings back for you your x discretization on the Chebychev points and builds all the components of this matrix. Okay? Now, once you have that first derivative matrix called D of n, then other things are pretty easy to calculate. You want a second derivative? What do you just do? D of n squared, right? You just square that thing. Now, important, don't put a dot there. This is not component by component. This is a real inner product of matrices. Okay? In fact, if you want the nth derivative, then you just take this D of n, raise it to nth power. Okay? Now, comment that we've already made before, this matrix is full. You can see it. All the components are there. Full matrices cost you. How long did your Cheb take to run on the homework? You guys remember? It takes a lot longer, right, than your FFT. What's taking it longer is the fact that you're working with this big, full matrix. You want to see a code go slow? Very simple exercise for you to do. I know, nobody wants to see a code go slow. But just to illustrate what would happen, take your homework 4 or 5, take the FFT part. Or no, actually, take homework 4. Remember we built the ABC matrices, right? And we did the SP diags on them. So we have ABC. They're like sparse. One line of code, just to see what the effect is. You know how you have matrix A? After you get A, B, and C out, just do this. Do that. Puts in zeros in all the places supposed to be zeros. Forces your code now to work with the full matrix. Even though it's going to have to just multiply a bunch of stuff by 0, what you're basically telling it, yes, please multiply by 0 to get 0 for everything that's there. Do that, and then, so you know how fast it runs without doing that, and then do that and tell me how that looks for you. That is the danger of full matrices. You see a huge difference, right? Because this now costs you order n squared to do one operation, like a matrix multiply, versus before you're paying basically order n. Okay? Okay. In this problem here, this matrix is full to begin with. And that's what costs you. But you get such improved accuracy that you might be willing to live with it. Okay? So you have to maybe use a lot less points.